So how many of you are familiar with Asterisk Scf, the Scalable Communications Framework? It's the interface that all of us developers have been drooling over for years. It's got this amazingly flexible API. It scales really well out of the box. It gives us low-level access to channels and bridges, mutes and sound injections. It builds off the industry-standard PJ-SIP stack. Fantastic system, amazing, absolutely incredible. We'll all be able to program it to do anything. Wait, did I say SCF? Right, no, I mean ARI. ARI will let us do all of that, and it's real. It exists. It's ready to be used, and it's been out for years. I think we're out of sync. Pardon me, let's see. Well, that'll work. Okay, so how many of you have actually used ARI? All right, pretty good percentage. I think we can say that ARI isn't really useful for everyone, at least not directly. But when you want to do something really cool with Asterisk, when you want to do something beyond the regular old PBX functions, ARI is the interface we've all been waiting for since the first rumblings of SCF. Finally, we have an API to Asterisk that is standardized enough and powerful enough to really raise Asterisk to the level of framework. It's an incredible tool, but like the idea of SCF, it really doesn't offer something for everyone. If you're building a PBX, you might as well stick with the dial plan. This is a big reason why ARI exists and SCF doesn't. ARI works with regular asterisks. You can use it alongside the dial plan, alongside AGI, AMI, all the tools that you already know and use, all on the same system, and simply use the best one for the job. It's true, we don't get everything that SCF promised. I'm still waiting for live call failover to actually work, but I'll settle for more stable and scalable asterisk, which is what we now have. So to understand why we need ARI and why I'm so excited about it, let's go back a few years. In the beginning, there was DOS, well, Tris-DOS to be exact. In this Tris-DOS, there was a game. This game's name was Paddle Pinball. Now, I'd played pinball before. It's kind of fun. There are all sorts of noises and flashing lights, colors, and the incredibly real feeling of a steel ball rolling around and hitting things. So when my father told me that he had a pinball game downstairs, I was really excited. The pinball game he showed me, though, had none of these other things. There was no color, there was no sound. The ball consisted of a little weightless square which teleported around the screen in a non-linear fashion. Much as this picture shows, though, it did leave a trail on the screen. These weren't exactly the modern gaming monitors back then. So you can imagine my disappointment at this bait and switch. That is, until my father suddenly pressed a key and the ball disappeared. Another key and one of the bumpers moved. And then one was added. A bonus slot was shifted over. Suddenly, a poor imitation for a pinball machine took on a whole new dimension. I could create my own pinball game. Asterisk is a lot like a pinball game. It has all sorts of bells and whistles, voicemail and call queues, sounds, IVR, and, well, all right, let's be fair. You can actually do quite a lot with it. You can build all sorts of things. You can move bumpers around, you can change the numbering plan, you can set up a call tree. It actually really is quite a lot like pinball, paddle pinball. Eventually, though, I got tired of pinball. I could build games which were played themselves, which would always win, always lose. I could draw pretty pictures and write out messages. At the end of the day, though, I was only working with a few set tools and a set field. One day, I discovered Linux. Okay, it actually took about a week to install, but it was one day that it actually booted. I'll never, ever forget that day. I had been stuck in the world of Microsoft, playing inside the pinball machine, not knowing about the world outside, and suddenly descended into this enormous cockpit to the world. I could do anything. There was a C compiler built right in. There was this powerful and completely unusable thing called VI. There was this bash shell, which made batch files look like a baby's rattle. Sure, I couldn't actually do anything with any of it, but I could feel the cool power emanating from every crevice. I wanted this power for myself. All right, so that's enough of the little vignettes. There's a common theme here, though. We crave control. We want power. We seek agency. If we're willing to give up on pretty pictures and point-and-click interfaces, we can find that power. And programming is what makes us creators. ARI gives us programmers the power and the flexibility to create. So the other partner in this talk is Go. I've spent many years programming in C, more than 15 years in PHP, several years writing in JavaScript for Node, and for the last 3 years, though, I've written almost exclusively in Go. I've been in the programming business long enough that one feature of code which rises above almost everything else is readability. Churning out code at a fast pace is great for getting a project out the door, but inevitably, eventually, whether it's just to fix a bug or to add a feature, you have to go back to that code and read it again and work with it again. So C is a very spare language. Very few visual clues about the processes. When you write C, you understand this, and so you create lots of commentary. It's not uncommon to have 5 lines of commentary for a single or 2 lines of C code. But it's also equally likely that that commentary is about 50 revisions out of date and has no bearing on the code whatsoever. Also, it's really nice to get a project done by the time you're dead. And so other languages are a little better. PHP, for instance, a lot faster than C to program. There's no typing. You don't have to worry about all of this kind of stuff, the visual clues. Unfortunately, it's a pretty broken language. Syntactically, it's painful, internal inconsistencies, and a number of things. So not really the best language for a choice of maintenance and readability from the sense of it's not a very clean language. Node, wow. I have yet to see any language where you can churn out code faster than in Node. Unfortunately, if you go back to that code 3 months later, woe be unto you for trying to understand your own code that you wrote. I don't care how many comments you set. And of course, as Jared pointed out earlier, package management dependencies that change every 3 months. No, thank you. So enough tearing down other languages. Go is amazing. I'm a little biased here, but Go is amazing. There's never been a language that I've worked with that's easier to read. I can give it to customers who've never seen Go before, and they can maintain it themselves. Even more importantly, I can read the code they've written. Incredibly, you can pick up random code from GitHub, and you'll almost certainly be able to read and understand it without getting a headache. It's a fantastic tool with all sorts of asynchronous operations, with allowing you to write in a linear and declarative style, even though it has multiprocessing and kind of node-style, event-driven architectures in a number of amazing ways. So it's got cross-compiling, static linking, fast compilation, powerful static code analysis, and incredible automation tooling, self-documenting, standardized formatting. Go is an amazing platform on which to build. All of this aside, though, this talk isn't to convince you to use Go or ARI. Instead, this talk is to show you how I use ARI with Go providing a gentle overview, and just maybe inspire you to try ARI yourself. Transitions are not going to work. Sorry. Oh, what do you know? There it goes. So when we embarked on our quest to build a Go-based ARI library, we were hit very quickly with a major problem. ARI events each have a completely dynamic structure, and we only know what that structure is by decoding the event and getting the type. Go is a statically typed language. It's a very strongly typed language. It doesn't allow you to simply, oh, decode that JSON, and then we'll figure out what it is in the structure. No, you have to define the structure in order to decode the struct into. So there are various pathways that other Go implementations of ARI have passed, usually involving some sort of either grand structure that tries to encompass all the pieces of every event into one struct, or trying to come up with the least common denominator of struct entities. So in our design, we decided to take a little bit of a different approach. We wanted to maintain the integrity of the structs themselves, the structures of the events, so that if you go to the documentation of ARI, the structure of those events matches exactly what the structure is in the expected fields within the events that you get in Go. To do that, we simply use a two-pass filter. So we decode once, extracting only the type, and then decode a second time based on that type into a defined struct. So fairly easy, fairly straightforward, but extremely flexible because it allows us now to keep the standard types for the events. Other problem with, not problem, but difficulty in ARI, and this is not unique to Go, is we have some conditionals that are kind of missing. So if you try and start a recording and something goes wrong, you'll get a recording failed event. Try and do that with a playback. Silence. Nothing. No idea. You get no error on the command. You get nothing about the playback failed, no event, there's nothing. You just simply don't get a playback started event, or you don't get a playback ended event. So you've got this. As someone else mentioned yesterday, music on hold is another one of these. You have no indication, no event indication that the events happen. Another similar problem, asynchronicity. So HTTP is inherently asynchronous. It's not connection-oriented. You've got a hit and a request and a response. Node, the primary language that the ARI reference language, I suppose you could say, very asynchronous. I mean, it's really an asynchronous world. The problem is async really sucks for most business logic. Trying to decompose a nice set of tasks into an asynchronous list of, okay, we do this, and then when we get an event, we do this. Okay, it's really efficient on the computing side, but it's really a pain to program in. So taking both of these problems, we look at Go's answer for everything, wrappers. So it's no exaggeration to say this is Go's answer for everything. Everything, even the base library, is composed of wrappers upon wrappers upon wrappers. And the way Go is structured makes this really easy. So we have built in the ARI library a number of wrappers that actually allow you to separate this asynchronous world of ARI from the business logic that you actually want to provide. Examples of these are playback. So basic ARI, you schedule a playback, you look hopefully for an event back saying that your playback started, or you'll have to time out if it failed and say, well, it didn't start after a second or two, I guess it failed, so we'll have to requeue it. And if it does fail, then you have to explicitly stop the playback, otherwise it's already queued in the playback, so it'll get stuck. And then you have to wait until it finishes so that you know when to process the next code. At any rate, a whole bunch of complexity. We expose a simple playback that is called as a synchronous operation, play this file to this channel, and I'm done. Return when you're finished playing. So when you're writing ARI code then, all you have to do is say, play this file, and continue. Another one. So Asterisk 14 now has the ability to play a sequence of audio, but if you're still using 13, it being the long-term release, we've also had an audio queue. It's a little bit more flexible than the native Asterisk 14 queues, but it basically allows you to create a queue, add files to that queue, and play the queue. Again, all synchronously, pseudo-synchronously. It runs in the background. If you want to run it in the background, you pass it into a Go routine, and it runs in the background, and you can signal and control it based on a control context, which is Go-specific language implementation, but it's an easy way to control a second-party thing. Another really common function in writing telephony applications is this concept of a prompt. That is, you play 0 or more clips, audio clips, and say this and this and this, and you compose this whole string. And if you get any digits within this entire playback, stop the playback and handle those digits. Or if you have more than one digit, you may want to collect, say, up to 5 digits, or you want to collect based on a pattern match of digits, and let the prompt continue playing until you have a complete match. All of this is encompassed, not to mention timeouts. Timeouts another big thing. So you get to the end of the message, how long do you want to wait for the next, for a digit to be played? Likewise, how long do you want to play after wait after the first digit to the next digit, and so forth? Do you want to match on the pattern? All of this is encompassed on a single function call in the ARI library, prompt. You can specify the options or simply take the defaults. The defaults are fairly reasonable. It takes waits for a single digit for, I think, 3 seconds, 2 or 3 seconds after the end of the playback. It'll stop playback immediately on receipt of the digit and continue on. You get back from this all the digits that were played during the prompt and the status of the playback, the status of the prompt, which is basically, did the digits that were dialed match? Did they not match? Did they create an invalid situation? Did it time out? Or did you get a hang-up during the prompt? So all of these are simply provided to you as the end. Recording, another issue. Recording in ARI, a bit of a pain, again, because it's asynchronous. We have some wrappers around recordings to make that experience much easier. So another key issue when building ARI is this connection conundrum. So essentially, there are 3 different ways, generally, that you can structure how ARI connects to, or how your application connects to Asterisk. The first is so small I can't read it. The single API, single ARI, which takes all the events for everything. So you have a single ARI application, everything goes through there, and you get the events to route somehow, somewhere. So this is really easy, but it leaves open the question of how do you get those events to the places that matter? You have this big event bus, say in Node.js, and you can listen on events and maybe filter those. There's no such construct in Go. You can't have an untyped bus that just transmits everything unstructured. The other option is application-oriented ARI. So you have one application, say, your voicemail. You have another application, say, this IVR tree. You have another application, and so forth. This works great in that you have the events somewhat filtered down, but it makes interop really difficult. So you're dealing with separate programs. You lose state between the transition of these programs, and it becomes very difficult to have a nice, clean flow throughout the system. Third option is the one ARI app per call. The idea here is calls come into a dispatcher. The dispatcher starts up a new ARI application for each call, and that call is handled by one application, one access point. This is really good for having scoped events. You know exactly the events that you're going to receive for every case. The problem is it really doesn't scale. ARI is really big on the consumption of TCP ports. When you start sending a whole lot of commands, you start chewing up a lot of your TCP ports. It's very easy on a busy system to end up with port exhaustion with this method. So each of these have their own advantages and disadvantages, but the problem is when you're writing these in Go, it's really inflexible to the places. So, what do we say? More wrappers, as usual. This is Go. So, we have actually implemented in the Go ARI library an internally typed message event bus. So, the way we get around the typing in Go is, as I mentioned earlier, we do a 2-pass decode. So, on that second pass, we have a full structure for an event, but we pass on to the event bus or the channel bus simply an interface that has one method, get type. Now, then when you get that message, you can map that based on the get type, based on the feedback of get type, and you can map that to a real struct by type assertion. Now, this sounds like another decoding, but it's actually vastly more efficient. All of the data structure is in RAM. All you're doing is changing the type label. So it's an extremely efficient operation. You're still only decoding the event once, and all you're doing is asserting a type when you get the type. So it's a really efficient way of getting standard events on a common bus that are fully typed in Go. The other concept is the idea of a subscription. So you can subscribe to a set of event types. Say, this routine is only interested in a stasis stop event when the channel exits stasis. Or this event is only interested in DTMF entered. This is an excellent way of scoping events then if you are stripped down to a single instance, a single call. We add to that the idea of entity subscriptions. So these are, you only care about events for this channel, or for this bridge, or for this playback. So if you subscribe to a set of events for this particular channel, you'll be guaranteed that any event on this event bus or on this subscription is scoped only to that channel, and will further be scoped only to the events that you request on the list. So in this way, it makes it very easy to get very finely tuned events on a very common channel. And lastly, we implemented another message bus gateway. So as some of you may know, there already exists a Go proxy which allows you to connect to a message bus and adapt ARI to that message bus back and forth for events and commands. So we did ours, again, a little differently just because ours came first but didn't actually come first. Long story. But anyway, it's different. But one of the key factors is that the message bus in our case maintains full decoding of the original source of the event. So it's fully structured. It maps exactly to the ARI Go thing. So another common feature, and this is the last of the theory, I promise, in voice is this idea of a state machine. A lot of voice operations map very easily to a state machine. But every state machine library that I've ever seen, I've hated. Has all sorts of boilerplate. You have to define what your states are and how they transition from one another. I'm sure it's really great for organization and for a manager to say, oh yeah, this is what this and this. I don't really care. As a programmer, that drives me crazy. It's so much boilerplate and so much pain. So I recently watched a talk by Rob Pike, who's one of the authors of Go, entitled Lexical Scanning in Go. It's a really excellent talk, as are most of Rob Pike's talks. But its key feature that I stole is his state machine, which consists of a very simple for loop that simply passes a state function back from one into another. So a state function being defined as a function which returns a state function, very recursive. So it makes the state machine extremely simple. It's 3 lines of code. For state function start until the state function returns a nil and execute the state function. So let's take a look now at some actual code after all that mess. So if I can figure out the manipulations here. There. Okay, that's not what I want. That is C code. All right. So. I think I'm just not in my tmux session. Oh, I'm on the local machine. That's what it is. I think I do need to clear because I can't see anything. Ah, there we go. There we are. Okay. So I threw away my code here. Wow, I wish I could see this on my screen. Let me see. That's probably it. App. There we go. Well, this Wi-Fi could be better. So, some real Golang here. So we have the main loop here. As you can see here on line 53, this is our entire state machine, 3 lines. We start at the menu state, and we continue until the next state is nil. We simply execute the state. So if we go down here to menu, this is illustrating the prompt that I was talking about. So we have a prompt that takes a context. Again, this is just a control structure. S.h here is simply the handler for the channel that we're working with. The nil here is referring to the options for prompt. In this case, we supply nil, which means take the defaults. And we simply supply the list of sound prompts to play here. In this case, they're all sounds, but we can use any media URI that ARI accepts, which includes such things as numbers, as dates, as digits. We've even got some helper functions that allow you to construct more elaborate sequences of sounds. At any rate, we get back, we return a if we get an error, we go to the invalid state. If we don't have an error, we check the status. So our status map to explicit types. So these are very clear and easy and mapped to the source code, to the static code analysis tools to very easily do autocompletes and states. So we can see very easily if we get a timeout, we simply loop back to the menu, play the prompt again, we check the number of tries and abort if we don't want to, and then we take a complete digit, which in this case means if we get 1 digit is count it as complete, we go down to run reply. So let's take a look at reply, which makes use of the audio cues, if my network hasn't gone away. It apparently has. Alas. So, while we wait on that, there we go. All right, so reply, this is how we use audio cues in ARI. So we simply declare a cue, as we do on line 87 here, and add prompts to the cue. We can do these add prompts all in one line, or we can add them discretely like I've done here for clarity, whichever makes it easier to read at any given fashion. Then we execute play. We don't care about any results because all we're doing is replying and hanging up. And we return nil to end the state machine. On any errors, we also have an invalid. This is using just our synchronous play operation, just simply takes what are we playing to and what are we playing, and returns when it's done. So very simple application. This is running, if you want to call it, at 888-240-0309. It'll run through this code as we watch here. If this network is at all fast. We'll watch there. Oh well, the fun of live demos. We're on remote machines. Let's just do it.
Hello. Please enter your number. UN2.
And that's it. Nothing to it. Very simple application, but the idea is you have very few lines of code that oh, look, it actually finally showed up. Very few lines of code, very easy to deploy, and easy to work with. So this is ARI, and we are trying to get it finally open source enough, or cleaned up enough for you to use. It's on its third iteration. This is the first iteration that has been publicly available. So that is, on the wrong screen. Let's see. There we go. So you can find it here at this URL on GitHub. We've done very recent release, very recent updates, but we're happy to take any help and certainly happy for any users. So I do have a question here from Miguel Angel Torres. Does ARI heavy usage affect voice quality? In my experience, no. So it runs through a fairly different process in Asterisk that I don't think has much to do with the voice. It is essentially the same as any other control processing in Asterisk. So there shouldn't be anything heavy enough in ARI to affect the voice quality, no. And so one other thing, we'll go into the deployment side of this application, which is deployed currently in Kubernetes in my talk tomorrow. And we'll go over more of the Kubernetes angles of this deployment and provisioning.